Okay, so today we will talk about reinforcement learning using human feedback, specifically using PPO. We will be implementing PPO from scratch. I just did. I will go over through the implementation, and then we will also look into the official TRL implementation of PPO from Hugging Face. And we can also look at why certain design decisions were made, because our implementation is inspired from that implementation. So we can look into the production grade implementation and our simpler implementation and compare also. Just to show how in general reinforcement learning works, and I can put this also in the description. In reinforcement learning, we have an agent denoted by this policy pi of theta. So theta is trainable parameters. Agent observes an environment. So it observes a current state denoted by S of t, and it takes the optimal action based on that state, which A of t, which affects this environment. And after taking that action, we get some reward R of t, and we get into some next state. And again, agent observes that state. Right? So you can think of a very simple example is, for example, a video game, right? So we have a current state of the video game where all the players are. And for example, the image of that video game is the current state, or all the pixels in the image is the current state. And based on that current state, the agent takes an optimal action. Or after taking that action, the game goes on to a next state, and it also gives you some kind of reward. Sometimes the reward is also not just on the next stage, it can be at the end of the episode. Right? So this is the standard reinforcement learning loop. And this is how it looks when you apply it on language models training. So in this case, for us, the states are the input prompts. So all the tokens in the input prompts are the states. Agent is again this policy. States are the prompts, and the token that it produces or completions are the actions. And based on those actions, it gets some reward, and there's a loop that goes on here. We have a base model which is trained on internet scale data. Then we have supervised fine tuning or instruction tuning, which is trained on the order of 10 of thousands of annotations, so the model knows how to follow a chat template or how to answer questions. So after this supervised fine tuning, we want to do the preference tuning, like we want the answers which are useful and not harmful to the humans. And there are two steps for it. We want to train the reward model first, and then we want to use that reward model to train the PPO. Just to show how the architecture looks like for the reward modeling, it is normally done by using auto model for sequence classification. It is just a wrapper on top of large language models where it takes the final logits of language model and append a linear layer on top of it. And using that, we can predict whether to the classification, whether this outcome belongs to the rejected or the accepted answer. And at the inference for time, we just take the logits from that model whose size is just 1. Just to also show the above loss function implementation here, we have the inputs chosen, which is the inputs here are query plus response, and we pass it through the model, and then we get a single scalar. Normally it is batch time scalar, so inputs are passed as batch inputs, and the rewards rejected are the rewards of the rejected output. So it is query plus rejected output response and pass to the model, and then we also get a scalar. And then similarly, like it has been written here, we take the log sigmoid. This is actually a bit more stable than doing sigmoid and then negative log, so it is more numerical stable to do negative log sigmoid, rewards chosen minus rewards rejected, and take the mean of that and train the model using that. So after the model is trained, we just pass the model the query and its output, and it gives a scalar for that, what is the reward of that input query plus the output. Okay, now let's go through the PPO pseudocode, how it works. And I will try to go through the same thing, but few different ways, through a diagram, through a pseudocode, and through the actual code, just in hope that it really makes sense to everyone. This is the PPO algorithm pseudocode, and there are three main steps to do PPO. And this is first an on policy algorithm. If you don't know, you don't need to worry too much about it. It only means that the policy that is optimized, and policy here means the LLM which is optimized, is the same policy which is also generating the data to be optimized. Right, so the initial model has parameters theta 0, and we have initial value functions at phi 0. I think I should also explain why we need the value function at all in reinforcement learning. Why can't we just optimize just the policy or LLM directly without needing the value function? And to just give a very brief explanation of it, if we don't have this value function, then what happens is that the reward model gives rewards after the complete answer. So we have a query and then we have a complete answer, and then you get a single reward, right? And this whole complete answer rollout is called Monte Carlo rollout. So after the whole episode ends, or after you get the complete answer, you get a single reward. So this reward is very sparse. So one way to avoid that is to use value functions, and the purpose of value function is to estimate the expected return given you are following this policy. So given a state, what will be the expected return of you being in that state following that particular policy? So for PPO, we have three main steps. We collect the trajectories, we calculate the rewards, and this is actually the part of the same thing. Collect the trajectories. By what I mean by that is you give the input queries to the supervised fine-tuned model or the initial large language model, and we get the answers from it. We sample the answer from it, and then we give the query plus sampled answer to the reward model and get a scalar reward for each uh, query answer tuple. So we save all of them in a buffer, also called replay buffer, and then we estimate the advantage based on those rewards. To balance between high variance and high bias, we compute the advantage estimate. And I can go through the what this advantage estimate does, but you can ultimately consider that advantage is is just a reward, but stabilized. So we don't have a high variance and we don't have a high bias, so somewhere in between we are. So we collect the trajectories, we calculate the returns, we estimate the advantage, and then is the main policy optimization and then the value optimization steps. And I will go through the loss function of it, but these are the three steps. We collect the trajectories, collect the rewards, collect the advantages, we do the optimization of the policy parameters, and we also do optimize the value functions. So value functions are also learned, right? So they are not fixed. So we want to ultimately improve what we predict will be the expected return of rewards from a particular state, given we have seen what the actual return will be. Okay, so this is a little bit more detailed compared to the previous pseudocode. So it is the same thing. I'm trying to talk about the same thing, but within different level of complexity. So it is really baked into the mind what this PPO really does, right? So after the next diagram, I will go directly to my implementation, which is highly inspired by TRL, and then we can also go to the TRL code, which you can really use to do reinforcement learning using human feedback on multiple GPUs at scale. Right, so what it does is, again, for that we have a policy model, which is a supervised fine-tuned LLM. And a bit more detail, we also have a reference model, which is just a copy or clone of that policy model, but it stays fixed. So it will stay throughout the training, its weights will stay the fixed as it started from supervised fine-tuning. And its purpose is that our fine-tuned or trained policy model don't stray too much away from the supervised fine-tuned model. So we don't want, because in RL what there is something called reward hacking. So policy can learn some kind of hack to maximize the reward, but really don't give some sensible answers. So we want whatever we have done so far after pre-training and supervised fine-tuning, we want to retain that knowledge We don't want to drift so far from that knowledge. That's why we have a reference model, and we will want to make sure that we don't stray too much by using KL divergence. We define an optimizer using NMW. We go through the maximum number of steps. We take a query from the data set. We use this policy model, not the reference model, but the policy model to generate the response from it, right? So typically what this generation means is doing the forward pass into LLM, and LLM produce the batch size multiplied by sequence length multiplied by vocab size, which is typically around 50,000 vocab size. Generation does an additional step of also sampling, right? So from all those logits of possible tokens, you don't just pick the maximum likely token, but you do some sampling on those tokens, so the answers are more interesting. And that's how you also get for RL the exploration part, because we do sampling here and then don't just pick up the most likely next token. The RL model can also explore other possibilities of token. Right, so in generation we get the response to the queries, then we score those responses and queries using a reward model. So remember, the reward model was trained in the beginning using the preference data which responds to human prefers, or basically it can also be done by LLM judge. So the input is queries plus response, and it gives a single scalar response to that query. And then basically we do the forward pass again, and then we calculate the log props and the values of the response only, right? So the log props, we only keep the one from the response, not the query part, and same for the values. So the values shape is also B. B is always is just the batch size for the efficient training, and the only purpose of batching is the efficient training and more stable gradients. So B is always in the front, and then the B cross sequence length, that is the shape of the values, and sequence length here is the length of the response only, not the queries. We get the values for both queries and response, but we just slice it just to keep the response, because those are the values that we are interested in. So when I will go through the code, you will know exactly what I'm talking about. So right now it's still a pseudocode, so you don't know exactly what shapes these are, but I will just go through this, and then I will just go through another diagram, and then I will go through the do the code itself. Right, after we have these log props, we also pass it through the reference model to get the reference log props, right? And we don't care here about the value function. And the reason we want to take the log props and reference log props is that we want to estimate the KL divergence from it. So like I mentioned, we don't want to diverge too much from the reference model. So we want our output tokens to stay close to the reference model. And this is done via reward shaping here. So we get the scores, which is a single scalar for each batch dimension. Then we pass it to the compute reward, which takes scores, log props, and reference props. And then we reshape it into the shape of batch size into sequence length. Then we calculate the advantage. And again, what the difference between advantage and rewards is basically balance the bias and variances in the returns, right? And we also get the returns, which will be used to optimize the value function. So all of these go to experience buffer, right? So we generate the samples, and then to make it more sample efficient, we do multiple steps for PPOs. Go through the n number of PPO epochs and use that same data set. Sample the batch from it. We sample the mini batch from this buffer, and we get all this out from the experience replay buffer. And now what we do is for the policy model that we want to train, we forward pass the queries and the responses. We get the new log props, and we get the value predictions, right? And then we calculate the loss for the policy, which were mentioned also in the previous pseudocode. We calculate the loss for value function. The total loss is the sum of value and policy. In the actual PPO code, there's also an entropy loss, which also basically encourages exploration. But here the exploration is mostly done using the generation, because in generation we are doing sampling. And again, sampling itself is a big topic. You can do top K, you can do min P sampling. So there are a lot of different samplings. So let's talk a little bit about PPO. PPO is a type of policy gradient method, and in specific it is on policy method. And what these policy gradient methods does is they can directly optimize the policy of the agent, or in this case the LLMs, which maps the states to action. And there are other kind of methods based on value function, which evaluates how good a state is. So agent can greedily takes the actions which maximize the value function. But for policy gradient method, we can directly optimize the policy using gradient descent. And for PPO, the general form of the gradient of loss is basically expected sum of log of action given state, and we multiply it with reward with phi. So phi can be a reward function. For example, at the end of an episode, at the end of the game, you get a reward whether you won or lose, but that can be of very high variance. So a general form of policy gradient method can be written like this. So it is expected value of log of action given the state, and we multiply it with also the phi. So phi in the most basic sense can just be reward, and then if this is the reward, then this becomes a reinforced algorithm. But the problem with the reward is that you get it after only for the episodic kind of settings at the end of the episode mostly. So this is very sparse and it has very high variance. So normally you also, what we do is we subtract some kind of baseline from it, and for us this baseline is kind of this uh, value function that we subtract from it to make it less variance, to make its variance less, but it is then high bias. And they have also mentioned it here, the return is calculated using Monte Carlo sampling. It returns, if the return is favorable, all actions are reinforced by increasing the probability of being selected, right? So if the reward is positive, then all the actions from T0 till T which led to final state, all of their probabilities will be increased. Okay, so and then if we look a little bit more into what an advantage is, so advantage is just how we can balance the high variance and high bias in the rewards. So in mathematically it can be written as the action value function, this Q, S and A minus the value function. An action value function represent the expected return after taking an action T at the state S, right? So it basically represents what is the expected value if I take the action A at state T, and we minus the value function from it, and that's kind of the advantage at that state and taking that action. Generalized advantage estimation, which balances the variance and bias. And when the lambda is 0, then this equation becomes this. The advantage function is just delta, which is RT plus sigma T plus 1 minus V of S of T. This is the TD error. And TD error, what it does is if we take an action A at a state S, it gives you a reward RT, and then we also go to the next state where we can take the value function of that state, and if we subtract it from the current state, that is the error, or that is the advantage in this case that we have of taking the action A, right? So this is how good an action at that state is compared to the average action in that state. And if the lambda is 1, then this becomes high variance, right? So basically sums up all the rewards from current position till the end minus the value at that state. Okay, let's go through the code. I think we went through a lot of theoretical part, but let's go through the code. Okay, so this is the main code. It's very small. It's only 400 lines, and it includes all the comments and also the inference part. So actually the meat of the code is very small, right? So, and it's highly inspired by TRL library, which we also have a brief look into just after going through this. So actually we can also have done it in a notebook. I just like to do it in script, and going through the Python debugger line by line and seeing what the shape of each variable is. And in my opinion, it works better for me, but you can also use the notebooks. So the first step for this is we build the model and tokenizers. So if we can go to the definition, it's quite simple. We have defined the model here, so we can use GPT-2. It's a very smaller model compared to the other LLMs. We could have also used a more recent model, Quen 3.6p, but for this purpose I'm just using GPT-2. You can easily switch it to Quen 3, but then remember to also add the chat prompt. This is a instruction fine-tuned model, so remember to add the chat prompt to it for it to work good. For GPT-2 you don't really need to add any chat prompt, you just need to tokenize and pass it to the model. But if you're using something like Quen 3 or any other instruction fine-tuned model, then you have to follow the chat template of that model to get the optimal results. So we have essentially four models. The first is the most important one, is the policy model, is the one that we want to train. The second is the reference model. It is the same as the policy model, but we will keep it fixed. It will not be updated. And we will train this one, but this one will just be fixed for reference, so our policy don't deviate too much from the reference model. Next, we wrap this policy model into policy value model. And the reason we wrap this policy model into policy value model is so we have to do the forward pass once. So we have already done the forward pass through the LLM, and then we can use the LLM's hidden state to pass it through the linear layer and get the values. So we don't have to do two forward pass, it will be redundant. And yeah, doing it like this, wrapping it into a single model, saves us one extra forward pass. Right, so we wrap our original policy model into the policy value model. Then we define the tokenizer, so all the input text goes to the tokenizer. We make sure that the pad token exists. For GPT-2, it does not exist, so we just make the pad token equal to end of sequence token. And why we need the pad token is for batch training, right, and batch inference. So if we have the input queries of different lengths, it will just make it of same length by appending the batch or by appending the pad token. So for example, one query is 7, the other one is 10. It will just make both of them of length 10 by appending 3 pad tokens to the query which has the length 7. Yeah, this is how we set up our models. We define all the models, then we define the data loaders, and data loader in this case is just IMDb data. So it's nothing special. So data in this case is just IMDb data. You can use any other data set. It is just to show how the PPO and reinforcement learning using human feedback works. We just load the MDB data set, and then one thing we do is tokenize all the data set. So we don't have to tokenize while training because that will be time consuming, not so efficient. So we normally tokenize the data set before training begins. We set the format of dataset to torch, and we keep the columns input IDs and attention mask. So one thing I should mention is important is in the tokenizer we are setting padding to true and also truncation to true. So what padding setting to true means is that it will set all the queries in the same batch to the size of the maximum query, right? So like I gave an example before, if one is queries of size 7, the other one is 10, it will set the size of both of them to 10 and append the pad token that we appended to the tokenizer before. And then we just add a data loader which the size of mini bench. right? So after we have loaded all the models, the data set, and here comes the main PPO loop. And what it does, it just goes to the data loader. We first roll out the mini batch or roll out the experience. And just going through the high level, but we also discuss in the pseudocode, roll out the mini batch and save the log logits of reference of the current model, the rewards of the current model. Then we can compute the advantage and returns based on those rewards. And after we have the advantage, then we do multiple PPO updates on that and update our policy value models using the clip surrogate loss function for policy model, and same for the value model. We also use the clip loss. Right, so these are the overall 3 steps. Go to the data loader, do the rollout, compute the advantage and returns, and update the value model and policy model. Now I will start going into the debugging and going through each of these steps and what it does. Okay, so the first is the rollout mean patch, and you can see the input to it is a policy value model, which computes the policy. So it contains our policy model or the LLM that we want to fine tune, and it also contains the value model which computes the expected return for each state, or this each state is the each token, right? We have the reference model which will stay fixed throughout the training, so our training don't deviate too much from the reference model. We have tokenizer, batch of data, and inference device. And if I go into this, you see we will save all of our experience in these lists, and it is the query response. This is the query plus the response we get from the model. We have responses which are just the response minus the query. We don't have query here, just the output response. We have log prob list, we have reference log prob list. So this is from the actual policy model. What is the log probs of the generated tokens from the policy model? What is it? Is it from the reference model which stays fixed? The sequence length. This is the generated sequence length, the values list, and the reward list. So these are all the things that we need. And if I come here, let's look into what the batch is. So right now I'm using the batch size of 2, so you can use any other batch size, and we can look into the shape. It is of 2 cross 71. So there are 2 queries and each one of length 71. I mean, the original query will have a different length, but since we are using padding, so both are padded to the same length. Then we do the context length, which is the query length, and which is the shape of at dimension 1, which is 71. Then we do the torch no grad in the context manager, because we are generating now. So we have now the initial policy model. We want to generate results based on query from that policy model, and then we will assign the rewards to it, calculate advantage, and then update the policy model to generate results which have better rewards, and minimize the probability of tokens which generated the bad rewards. Right, so the first thing we do is do batch generation. The generation will be of different length, similarly as the query is of different length. The number of tokens which are generated after generation can be different. So using batch generation, I can go to it. What we essentially do is we pass it through the LLMs. We go through each query and generate the response. We also get its logits. Actually, we will ignore it because we need to pass the same query and response through value policy model. So after we take the responses from it, we pad the response on the right hand side with the padding values. We do the same with the logits, and the reason of doing that is essentially so we have the output of the same length, so we can process it in the batch efficiently. Right? So let's see what happens. We get the generated IDs, and let's look at into its length. So it's 2 cross 121. Right, so remember the context length, the input query length was 71 and the generated is 2 cross 121. So this is input query 70. Sorry. So this is the input query 71 plus whatever is left, 121 minus 71 is the number of new tokens also in there, right? So the response contains input query plus the output query tokens. And in this generation, we use the generation config. So basically all the configs that you are aware of that we normally use for generation, we do generation by sample. Now we go through each batch size, and this is a simplification that I did. It's not very optimal, and that's why it's just for education purposes. So for each batch size, I'm going one by one, but essentially you will not do it in production, right? But just for educational purpose, it's okay. But for TRL, this thing is a mini batch, not one by one going through it, but the results are the same. So essentially I get each generated ID. So remember the size were 2 cross 121. So I get the first one. I go through the, since I'm going through the batch size, I append this query response to this list. So this is a part of our experience now. We collected the query response from the model. Now since we generated the outputs of the same length, so we need to figure out where those paired tokens are so we can remove the effect of those tokens in the downstream task. So this is what it is, generated ID wherever it is not equal to paired token, and then convert to long, so it is kind of integer. So it will be 1 wherever it is not equal to paired token ID, and 0 when it is equal to paired token ID. We are going to pass this generated IDs, which is again query plus the response. Its size of 1 cross 121 because we are going through each batch, and we are passing it also the attention mask, right? And what this PV model will does, as you can see, it's defined here. It will pass it through the LLM. So it will first pass it to the LLM or GPT-2 model with this attention mask, the input IDs. It will get its hidden state and also get its values. Let's just do the forward pass to see what the outputs are. So outputs are a tuple, logits, and values. And if I go through it, so you can see the logits is 1 because batch size is we just going one by one. 121 is the sequence length, and this is the vocab size of 50,257. And then we have the values, which is 1 cross 121, right? So this is for the entire sequence, query plus response, we get the value. Then I have some debug prints here, but let's just go over through it. And now we are trying to remove the query part from generated IDs. So remember the query part was still context length. We are taking everything context length till forward, right? So this will keep us from just the generated tokens, which is 150. So we are generating the tokens in batch generation using this function generate. And inside that it is using the generation config where it uses temperature to divide the logits. So to match the generation configuration, here the logits that we get, we also will divide with the temperature. So in the simplest sense, you can keep the temperature to 1, so it does not do any difference. Now, this is interesting that the selected logits is context length -1 till -1, right? And this goes again to the heart of how autoregressive modeling works. So for each token, we predict the probability of next token, right? So that's why the first token, which is as context length, its probability is given by the token before it, and that's why it is context length -1. And likewise, the last token probability is given by the token before it, right? So this is context length -1 till -1, and we will do the same for the reference logits. have some assertion that the shape of the select widgets and generated index is the same, like the size is the same. So we have subtracted -1 from here, but we are also going -1 here, so the length stays the same. Now this here we are doing two things. First, we are doing the log softmax, right? So what it will do is convert this selected digits, which is again of shape 150, 50,257 into a valid probability, right? So log probability, sorry. Still 150, 50,257. But we don't want that. We want is to select the log probs of the selected tokens which were generated. Right? So we give the index of generated index unsqueeze to -1, so we can select on the last index. So what it does is it will select each token which was generated its log probability. Right? So the final answer will be 1 cross 50. So the log probs is 1 cross 50 like I mentioned. So it has selected the generated index token from the log probabilities. And you can play around with it to see how torch gather works. It basically gathers the values which is given by the index here. Now since we have the log probs, we also want to get the reference probs to calculate the KL divergence, and it is actually the same method to do this. We pass it through the reference model. Reference model is passed with the generated IDs and the attention mask. Generated ID, remember, is the whole query plus response. This gen index is just the generated response, but generated IDs is query plus the response part. And then we just keep the one which is the generated part, which is after the context length, or for the autoregressive this is one after the this is one before the context length, right? So this is context length -1 till -1. So the same thing like we discussed above here is the same thing happening here. And then we calculate the, so this is the logits, we convert it into log softmax, so it is log props. And then for the index we also use the same gen index and calculate the or select the log props for those generated index. Now values is also of size 1 cross the entire query plus the response part, 121 tokens. So remember the input query is 21 tokens and the output response is of 50 tokens, and the initial values contains the values for entire query plus the response tokens. Just like the logits, we want to get the values using this. We have trimmed it down to the length of only generated tokens, and just like the logits, we are doing context length -1. Now we are getting the padding mask. Because we have using padding IDs for badging, we want to just keep the generated IDs which are valid and not just padded on. We are taking the first occurrence of that mask, so you can imagine that we have output tokens from a query 12, 13, 36, and then we have pad token of, I don't know, 50,000. 50,000, it needs to give 50,000. Maybe it needs to give the 3 paired tokens here for the response to make it of equal length of the other response. So we don't want to get all the index, we want to get the first index, right? So first occurrence of this paired ID, and this is what this part does of argmax, first paired ID. And now we are checking if there are any paired token IDs in the response. So they can be there. So if there are 2 responses, one will be padded, one will not be padded, because that's actually already the max length that we want the other one to be padded to. If that's the case, then the first paired ID is actually the whole length. Actually, let's just go through this so you guys know what's going on. We have the pad mask, which is of the same shape as generation, right? And it is basically false, false, false. Maybe I should print it out. Okay, so the first paired mask is wherever the generated ID is equal to tokenizer pad ID. So in this particular case, it's all false. You can see here because this one was not padded. So the pad mask is of shape 1 cross 50. First pad ID is of size batch. We're just taking a batch of 1. And we are checking if there is any pad token in this response, which is false, right? So we don't have any pad for in this. And if we don't have, then the first pad is equal to the length of the sequence, pad mask or shape 1. Right, so the first pad here will be 50 then. It's of size 1, but the value is 50 here, right? And sequence length is first pad minus 1, and the reward I'm generating very simply, it is the sequence length divided by, to normalize just this reward, I'm dividing by the maximum number of tokens allowed, which is 50. I've just randomly put it 50 there. Actually, I think I made a mistake here. So this is 1 minus, right? So sequence length, this needs to be 1 minus sequence length by generation by max tokens, right? So I want to encourage this response of smaller size or smaller length. And what I was doing here before was sequence length divided by maximum number of new tokens which are allowed. But that will encourage the reward will be higher if the sequence length is higher. Right? So what I essentially want is 1 minus sequence length by max token. So this ratio will be maximum 1 when the sequence length is higher, and then the reward will be 0, and we will give it the minimum reward of 0. And if it is sequence length is very small, like 0, it will get the maximum reward. I think we can do some kind of reward hacking here, so it can always generate the sequence length of 0 and gets the maximum reward. But then we also have a KL divergence term which avoids the policy to exploit or do this kind of reward hacking. But I think it's ideal if we do some kind of epsilon here, but it's okay for now. Then we also check if an end of sequence token exists in these generated IDs, right? So if it doesn't exist, then we minus a certain reward from it. And the idea is that as the model was unable to finish in time, for the expected number of maximum tokens, it did not generate the end of sequence token. So it did not finish its response in maximum tokens. So subtract the reward from it. So it did not do very good. So it should have completed response in the given budget of maximum tokens. So after all this, we collect all these log probs, reference probs, the values, rewards, sequence length, and responses. We collect them into a list. We concatenate this list across the axis 0. So we now have a tensor instead of a list. Finally, here we mark wherever the log probs, reference probs are invalid due to padding. We mark them invalid, right? So, and also the value functions. And this is one kind of a design choice that you can do. We could have also done this in the loop here, but it is more efficient to do it like this after we have concatenated it in forms of a tensor. So you don't have to loop through these operations. You can do it single shot, and these kind of matrix operations or tensor operations are much more efficient, right, than doing those operations in loop. Just going through what this does is, if I can go through this. Right, so we are here, and you can see the log props now will be 2 cross 50, right? Let's look at the shape of these. Yeah, log props are 2 cross 50. The reference props will be of the same as the values, 2 cross 50. Scores, you have to remember that scores are for the whole response and query. You get one reward. For this, we did not train a reward model like I showed, but I'm just taking a fixed reward based on the size of the output, right? So you can do that. So here we first define the invalid log props, which is 1. So why invalid log prop is 1? So the range of softmax is from 0 to 1. Right? So log of 1 is 0, and log of anything less than 1 is negative. So the values of log props are negative till 0, right? So 1 cannot be a valid log props. So you can put any value here, we will not be using it, but just to show that this one is invalid log prop. Right, so first what we do is we generate the response indices. We take the torch A range from for this size, which is the sequence length. Right. Let's go through it. What it does, it generates the response indices, and it is 1, 2, 3, 4, 5 till the response length, which is 50. Right. So it generates 1 cross 50, then it repeats it across the batch dimension, and that's how we get 2 cross 50. And then we see where the response indexes are greater than the sequence lengths. And remember, we got the sequence length like this. We get the first paired token, where the first paired token is, and we do -1, and that is the valid sequence length for our response. Right? And then we see wherever the response indices are greater than sequence length, so it goes for each batch and compare it with the sequence length of that batch and generate the padding mask. So wherever that padding mask is true, so it will be false for all the cases except for the padding tokens where it will be true. It will fill those torch mask fill will fill those log props wherever that padding mask is with invalid prop, right? So what torch mask fill will do, wherever the padding mask is true, it will fill it with the invalid log prop. And like I mentioned, it will be false for most of the output tokens except for the ones where we have the padding mask. We do it same for the reference log props. For the value method, we have this sequence length P1, and its P1 is the paired by 1 token or extra 1 token is sequence length +1. And you can see why that is the case by looking at this diagram. Right. So TD error at any state is the reward given the action at that state plus value at t +1. Right. So we need one extra value function for that, and normally for the last token the next one is just 0, but in general we need one extra value function, and this is also called bootstrapping. So you get a reward of taking an action A at state t, and then you also discount the next value at t +1, and we subtract the value at st, and that is the TD error. Right, so that's why we do t +1 for value function. So whatever is above t +1, we fill it with the value 0. Right, so whatever is below beyond this t +1 mask, we set it to 0. Then we return all these things, right? So we return log props, reference prop, values, scores, everything returned. So this was the rollout mini batch. The next one is to calculate the advantage, and the final one will be to calculate the PPO update. I will go a little bit faster through the advantage and PPO update because it is very similar to what we have discussed in the theory part before. Okay, so the next step after we do the rollout of mini batch, we collect all these entities. Okay, so the next step after we do the rollout of mini batch, we collect log props, reference log props, values, scores which are the rewards. We collect all of them, and then we compute the advantage and returns. And if we look into what the advantage does, so essentially it does the same thing as I described in this diagram. So if we go here and look, it essentially computes the KL divergence between the old policy and the reference policy. Right, so it computes the KL divergence, and the KL divergence computation is the approximation here, and then we subtract it from the reward model. So basically reward is given as a single scalar to query and response. It's a single scalar reward, and but to do it or distribute it to all the tokens, we also subtract the KL divergence of between the supervised fine-tune reference model and the old policy model. So in this way we don't deviate too much from the reference model. So if our deviation is higher, then we subtract more for the reward, or we get a smaller reward as compared to if we stay close to the reference model. Right, so this computes the reward, and then we get the GAE, or generalized advantage estimation, using these formulas. So essentially we compute the TD error at each point. So it's a recursive formula. So for each point, or for each time step, we calculate this TD error. So it depends on the value of the next time step and minus the current time step and plus this reward. And then we plug it into this GAE formula, and then we get the advantage of that state and taking that action. The return is just the summation of this advantage plus this value function. Just to go a little bit more into this generalized advantage function, estimation function details, we discussed it a little bit previously, but essentially it's the same formula as we discussed in this previous diagram. It's a recursive formula where this is calculated for each TD error, and this TD error is given by this, right? So at each timestamp we get the reward of that timestamp plus discounted value of the next timestamp minus the current state of the value function, and that's the TD error. And you will see in the code exactly this thing is calculated. So first we have the KL coefficient, like we scale the KL divergence. So log R is just the minus, this is the estimation of KL divergence. We minus the log props of the reference model to the old model, and then we take the negative of it, and that's the KL divergence. We multiply it with the coefficient. So this is how we scale this KL divergence. And then essentially what we do is we take this KL divergence, and then we just calculate the actual start, which is of the size of batch. So right, so this is a range of rewards of size 0, which is the batch size. So it goes across all the batch dimension, and it gets the actual end, which is wherever we are less than the sequence length p1, right? So remember, the sequence length p1 is the actual length of the response. So we have a query and we have a response or generation from LLM from it. So this sequence length p1 is minus the padding token plus 1 for the bootstrap. This is how we shape the reward. And now the reward shape is, so these rewards, the initial reward from the reward model is a scalar, but this reward will now be for each token. Okay, let's just run the code and see how it also looks like. We have the reference log prop, which size is of 2 cross 50. So 50 is the generation length. And we subtract the log props of the old policy model, and it is of the same size, right? And then we just clone this KL divergence. So this is non-score reward. So this is just from KL divergence, this reward. Then we get the actual start, which is just of size batch. So we have a batch size of 2, so, and it's a 0 index, so we have a 0 and 1. And then we get the sequence length p1, which is of size also b, batch. And we just add 1, so we get p1 length. And this actual end is, we just take the sequence length p1, and wherever it is less than reward, right? So if the padding length is less than the generated length, so it means we have a padded tokens, then we take the sequence length p1, so that is the valid length excluding the padded tokens. Otherwise we take the sequence length, right? So if there are no padded tokens, then the actual end is the end of the generation. And for all of these we add the scores to it, right? And scores are from the actual reward model. So this is the KL divergence term. Then we calculate the generalized advantage estimation. And what we do here is actually go in reverse order, right? And the reason for this is that this is a recursive function. So if we can have a look at it again. So we want to do this, and so actually we want to calculate this equation of advantage function, but this includes this TD error, and this is recursive. So you can see that at any time t, it depends on the current reward and the value at the next timestamp, right? So it is recursive. So if we calculate it from the end, then this value will be 0 at the end, right? So there are no further generations. So this will, we can easily calculate this part. The last part we can calculate, and then if we go from end to the beginning, it's much easier. Otherwise, from if we want to go from beginning to end, we have to calculate this recursively. It's more expensive, right? So it's much easier to do it if we do it from the end. Right, so it is essentially, if you look at it, it's the same equation. So the next values is the values at t plus 1s, and t is we're starting from the end. So the first value will be 0, right, because we are at the end of the value, so that there is no next value. And then we have this delta, which is exactly this. Delta is rt plus gamma v of t plus 1 minus v of s of t. So this is the same thing, rt plus gamma into v of t plus 1 minus v of t. So it is the exact implementation of that equation. Just the tricky part is that you go from the end to the, and then we just accumulate it, right? So we have this delta, which is the one that we have currently calculated TD error, and we add the gamma into lambda into last GAE, which initially it's just 0, right? But then we just add it, and this is this summation part, right? So this is exactly the same, except we are going from the end to the beginning. And once we have this, right, so we have all these advantages, and once we have this, we just append them to this list, and then we just stack them, right? Now these are the advantage, right? So, and this is used to train the policy model, and then the return is the advantage plus the values, right? Return is the summation of advantage plus the value. So, and these returns will be used to train the value model, right? So we have the current value estimations at each state, and then we want it to be as close to the actual return estimation. So we want to minimize the mean square error between this and whatever is the current value estimate from the value model. One other thing we will do is just mask the invalid advantages, right? Wherever we have these padding values, we give it the advantage of 0. One thing from all of this to remember is that the actual reward from the query and the response was a single scalar, right? So it just gave a single value of how good our response is given a query. But now the advantage is of shape of the same shape as the generated token length, right? So 2 cross 50. 2 is just the batch size, so 50 is the number of tokens. So we are giving advantage to each token, and because of KL divergence, we distribute this single scalar reward to all the other tokens, right? So, and then we just return the advantage and returns. And the final step to all of this is this PPO update, right? So this is the final step of this algorithm. So PPO update is also quite simple. All it does is essentially implements this PPO clip objective function and the value objective function, right? So this is the reward that we just returned from the advantage and reward calculation, and for just going to the value function, the loss for it is the current value estimate minus the actual reward at the current time step, right? So we just take the difference of it and take the square, so this is just the MSE loss. And the PPO objective seems again a little bit complex, but it's actually quite simple. And again, the idea is that we don't want to update to a very big step, right? So if the advantage is high, we want to estimate all the actions that led to that advantage to increase, right? We want all these actions are the tokens essentially of the generated sequence. We all want all of them to increase, and we want all of them to increase, but we don't want them to increase too much, and that's why there's a clipping here, right? So what a very basic policy gradient method does is just have the log of action given the state and multiply it with the reward or with some advantage function, right? So, but essentially the difference here is that we don't want it to change too much. So we first take the ratio of the new policy and divide by the current policy, and we estimate how much good a certain action is compared to how much more likely a certain action is compared to the old policy, and then we multiply it with the advantage, and if advantage is positive we want to increase the probability of all the tokens. If it is negative, then we want to decrease the probability, right? But we don't want to increase or decrease too much, so we introduce this epsilon which dictates how much it can increase and decrease, right? So this value, so this will also be multiplied by advantage, is clipped by 1 minus epsilon and 1 plus epsilon, right? So essentially all it does is stabilizes the training, and it's also mentioned here the clipping act as a regularizer, limiting the extent to which the policy can change. And let's just go over to the code how it works. So we define this epsilon clipping range 0.2 here. We define the value function coefficient. So this is where the final loss is the sum of the policy loss plus value function loss. And we define the number of epochs. So to be more data or sample efficient for all the things that we have collected so far, remember, so we have collected the advantage, returns, response, log props for certain queries, right? So we had this data set and then we pass it through the model and calculated all these items from it to be more sample efficient. And this generation process is the most expensive one in PPO, is how to get this generation. So once we have those generation, we want to utilize it maximally. So that's why we do multiple epochs for the same experience, right? Before we update, before we go back to the initial part of collecting the data again or doing the generation again. Just to be maximally sample efficient, we have multiple number of PPO epochs. We go through all these epochs. We randomly select a batch size, which for our case is just 2, and then we just select this advantage response, query response, log props, returns, and values from those mini batch index, right? So if we just go through it and show you some of the values, it's just 2 cross 50 because for us the mini batch index is just 2. So yeah, it will just be the same as I've shown before. Then we calculate the attention mask, all the tokens except where we have the pad token. And the reason for doing that is we are going to pass it again through the PV model, and we have the query response. So again we are passing through the model the query plus the response and the attention mask, and we get the logits and the value estimation from it. Again we will do the same thing as we have done in the rollout phase. So the difference is here is in the rollout phase we just collected the data from the policy in the rollout step. We didn't optimize the model. Now we will collect the data and also optimize the model. So in this loop, this PV model and its outputs will keep changing because we are doing gradient descent here. Again, get the logits in the size of the generated length. We divide the logits by the same temperature that we use to generate the tokens, the new tokens. We gather the new log props responses or by the generated indexes, right? And then we basically mask fill the wherever we have the padded mask to 1 because 1 is invalid log props. It can only be 0 or less than 0, right? And we do the same for the value function which we just wrote, right? So the first thing we will do is calculate the loss of the value function, and then we will do is the loss of the policy function, right? And the first thing we have, so what will be the easiest loss to estimate for the value function? So it will essentially be the v predict. So whatever our current value estimation is from our value model minus the MB return, and you can square it, so that can be the loss function, right? So that is the unclipped version. That's a valid loss, right? But it is a bit unstable, right? So MB return is, we are getting, if you what is this value? So this is the returns that we want it to be close to, and MB return we are just getting this mini batch of these returns. So that will be the unclipped value prediction loss. But for us, we don't want it to change too much. So what we do is we have the value prediction, and then we have the values from the previous step, MB values. So this is during the rollout step. We also get the values, and we want it to be clamped between these values, right? So whatever the previous value were and some clip value range from -2 to +2, we want the new value prediction to be in between this. If it is higher, then we just clip it to the maximum value or the minimum value. Right, so then we have the VF loss one, which is the unclipped loss, right? So we have the current value prediction minus the return and the whole square. So this is a standard square error, and then we have the clipped loss, right? And then we take the max of VF loss 1 or VF loss 2. In the actual formula, it is actually the minimum mentioned here, but since this is, we are calculating the loss, so, and here in this they don't give the clipped value function loss in this paper, but we are using the clipped value function for more stability, and this is how it's also implemented in TRL. But I just wanted to show why we have the max, because we are converting it into loss function, so we want to minimize the loss, right? So, and then the min become the max if you want to do the reverse of that, right? So this is the and then we take the mean to get a single value for it, right? So if we go through it, then VF loss is a single value across all batch. Right, so it has no size, its value is 2.973. And then let's move on to the policy loss. Right? So again, what we are trying to achieve here is this equation. The only difference is that we want to minimize this. So if we multiply everything with minus, so this min will become max, and this will become negative this, and negative, everything will be multiplied with negative, right? So otherwise, it's the same equation, because we are trying to minimize the loss. We want to calculate this ratio first. So we have the log props from the current policy model. We have the log props from the previous policy model. So if you take the log, then this division can be done as subtraction, right? So this division is converted, since we have the log props, we can estimate this ratio as a subtraction, and then to undo the log, we take the exponent of this, right? And then we get the ratio. And you can see here, the ratio shape is the same as 2 cross 50. So it's important to just know what kind of shapes we are working over. What is the shape of the results? That's the most important thing for me to understand this. What is the shape of this? And then we will do exactly the same thing like we did for the clipped value function loss. The first loss is just this ratio multiplied by negative advantage. Like I mentioned, we will multiply everything with negative, and the min will become the max. And we will also clamp its value between this clamping range and take the max of it. And then we have the final loss, right? So and take the mean. So we have a single value. So we have 1.4, and the total loss is the policy loss plus some scalar coefficient multiplied by the value function loss. And again, in the original PPO algorithm, as you can see in clean RL, there is also an entropy loss. For us, we are doing that using the sampling of the elements. And we do the loss backward. It calculates all the gradients of these loss functions, these two. Then we clip the gradients, take the step in the optimizer, which means essentially that we update the parameters, and then we zero out the gradients. Okay, so that's it. So just to summarize, we have the rollout of mini batch for PPO, where we roll out the experience or get the experiences in experience buffer. Then we compute the advantage and returns, and then we do the PPO update, which updates the policy and the value model, right? So right now I have a breakpoint, but yeah, we can remove that. I will show you that it runs, and you can go into this repo, learn from scratch, and this one is PPO from scratch. Okay, so it's running. So each batch or experience that we have collected goes through 4 of PPO epochs. Okay, that's it. And then let's actually, one more thing we should do is I will go through the TRL implementation of it, right? So, and you can see the similarities, and actually it's very similar, or if not completely similar. Let's just go through it and see how it works, right? I will put a breakpoint here just to go inside this PPO trainer and see what it's doing. So essentially it first builds up the models, build up the policy, reference value and reward model. Again, I'm not using the reward model here, but you can. It generates a data set and build the PPO, and I can. So this is all the configs of the PPO. It's a very nice way of specifying it. Models, reward model, value model, policy models here. Then you can train it. If I go into step into it, we can see what it's doing here very briefly. So it's these is mostly, this thing is just the multiple GPU stuff, and yeah, you can see what it's doing here is going the total number of batches. So the first step again is the rollout step, where it will pass the queries through this model and calculates or get the response for those queries and the logits of it. So they are using the logits here. I'm using the logits later or recalculating them, but this is more efficient. Yeah, after they get this, they get the logits, log props of it, and doing exactly the same thing, right? So they are cutting the response part from the context length till the end, and doing the same. They will be doing the same for logits also. Right, so for the reference logits, they're also doing the same. Actually, for logits here, since they are getting it from this batch generation, it's already of the size only response, right? But yeah, we are doing it later, and we have to cut the logits to only the response part. But for reference logits, they are getting the logits for both query plus the response, so they have to cut it only to the response part, not the query part. And they are essentially doing the same thing, dividing by the temperature, doing the log props, and getting all of these things, get the reward from the reward model. So this, for us, this reward, we don't have the reward model. We have to find our own reward, which is the smallest response will be better. Let's just see what their reward function does, right? So if we go here, so the first, it returns the reward logits. So essentially it passes through the backbone, and then it passes through this score. It gets the hidden state of it. Let's just go through what its shape looks like. Yeah, okay. Okay, batch generation is the same thing that we have. Then we have oh, oh yeah, we have to go here, right? So this output hidden state look like, so there it is for the each step of the GPT transformer. We have 12 layers, and each one has shape of 8 cross 77. Remember, we have changed the model, so now this is changed cross 768, which is the hidden dimension for GPT-2 model. So this is not of size vocab, so this is the size of hidden dimensions. And then essentially we pass it to the score, which is the linear layer, right? So if you look at what score does, if I just hover here, it's just a linear layer with input dimensions of the hidden layer and output of 1, right? So again, the reward is a single scalar, that's why its output is just 1. And you can see the output is 8 cross 77 cross 1. and this can be used as the value function, right? So this is, since this is for the whole sequence of tokens, and the actual reward then we get, which we want as a single scalar, will be this. So this is for each batch, you get a single reward at the last token, right? And the last token we are getting is by first true index, where we are not the paired token, and we subtract -1 and also sum up since this is the length, we want to add the index plus the length is the last token, right? So this part will be for value function, value estimation for each token, and this one will be the reward, which is a single scalar, right? So the score will be single scalar. So since the batch size here is 8, so it's just the output is of 8. If it was 2, we just have 2, but the full value will be of also sequence length, right? So if 8 batch size, 77 sequence length, and then the one also the last dimension. Right, we save all this in our experience buffer just like we did in our implementation, and I will just quickly go through it. It's doing exactly the same thing. We calculate the reward and the advantage here, again considering the masking of the paired tokens correctly. We don't want to attend to them or include their reward or advantage or their logits in our calculation, so we mask them out. Here we are going the reverse, in the reverse direction to calculate the advantages. It's exactly the same, actually I just called it from here. They are doing an extra thing which is optional, but it can greatly enhance the stability of the training, is mask the advantages, which is basically standardize them, minus the mean and divide by standard deviation, so it's a nice quotient of these advantages. Right. So we have a rollout so far. We computed the rewards and advantages. So it's the second step, and for us, the third step is to do this for number of PPO epochs and get these experiences that we have so far and update the value model and update the policy models, right? And then this is just for logging, and if there is gradient accumulation, like I mentioned, you can run it uh, many times before doing the zero grad. Okay, and then we have a lot of this is logging. So interestingly, they also log the entropy, but they don't include it in the loss function. Okay, that's it, and that's how the TRL implements it. So yeah, that's all. And the next time I will go over through also GRPO trainer and GSPO, and so those were really the landmarks. And what they essentially, very briefly, GRPO does is remove the value function part, and there's some nice intuitions why they do it. And DeepSeek also showed that you can use just the base model and then train the RL on top of it with verifiable reward. That's very important. And then you can also get a reasoning model on top of that. But if you train from start from supervised fine-tuning model, you can again use verifiable reward and also train a reasoning model. So yeah, next time let's talk about GRPO and the reasoning models, and that's it for now. I will link all these things that I have shared so far in the description, and let me know if you have